Good day, guys. Um, Welcome back to the fourth session of the Diverse Note Mobility Front End Development Program. Today, we will discuss the Module 5, and this would be the Part 2. So, here I'm going to share my screen with you. Right, so here this the arrays of pointers as multidimensional arrays. So here's the arrays of pointers. There is nothing preventing array elements from being pointers. Imagine that we need a dynamic array. The array is two-dimensional and we can't predict how many rows or columns it will have. We only know that the number of columns is stored in the columns variable and the number of rows in the rows variable. We are not going to attempt to allocate the array in the following way. So int asterisk ptr tab is equals to int asterisk malloc memory allocation rows asterisk calls times size of and then in parameters of it is integer. At the first glance, this might look like quite reasonable, but getting around this array would in fact be very complicated because the compiler doesn't know anything about the size of the rows at compilation time and won't be able to generate the correct indexing code. The array relies on us to do the work. If we want to access the element in column C and row R, we would have to calculate the pointer to the element as follows. PTR tab plus columns or cols times R, then this is inside a parenthesis plus C. This is due to the fact that C language arranges two-dimensional arrays row by row. The array begins with the first row, then the second, and so on. Consequently, to get to a particular row, you have to skip over all the preceding rows, and this is what a cols times R is intended for. Note that the numbering starts from 0. Next, you have to skip to the element in column C, and hence the plus C. This is not a very satisfactory solution, at least to us. We definitely prefer to use a clearer notation like this. Take note of this. PDR tab R then C. Is it possible? Wait. Yes, it is possible. This is how we do it. To avoid the inconvenience of skipping over the subsequent rows, we will store the pointer to the beginning of every row so we can reach each row without any acrobatics. How do we store these pointers? In the array, of course. We will call it the array of rows. Every row will have as many elements as columns of the desired array. Every element in the array of rows will be a pointer to a separate row. We need one more pointer to point to the array of rows. We called it PTR tab. Let's look at the figure illustrating the essence of our idea. So here, we avoid skipping the subsequent row, and we call this row as our array of rows. And every element in the arrays of row will have a pointer to a separate row. And this is called PTR tab. This one. So what is the type of the variable PTR tab? First, let us say that what type it is isn't. It's certainly not a pointer to an int asterisk. This is because the result of the referencing the PTR tab is not an integer, but a pointer to integer. This means that the type of PTR tab is a pointer to int, which is denoted as int asterisk asterisk. So this one is a pointer to pointer. So we denote it as like this: int, the int type, and then double asterisk, which is pointer to a pointer to. We can write a complete declaration now. You can see in the editor window. Yes, this is example of that. Once we've declared the pointer, we allocate the array of rows. Look at the code in the editor. This is how we do it. Right, so here, let us explain the meaning of this clause. Firstly, the pointer returned to the malloc. Here, this is the pointer. Return to the malloc. Surrender is converted to the type int and assigned to the PDR tab. Where's the PDR tab? This is assigned using this assignment operator. Secondly, the element of the array of the rows a pointer to the rows. So their type is int asterisk, and hence the size of the array is expressed as size of int asterisk multiplied by the number of rows, right? Finally, we need to allocate memory for every row and store the resulting pointer inside the right array of the array rows. Definitely the easiest way to do this is to utilize the loop. Look at the code in the editor. So in this code in the editor, we utilize the for loop, using the for loop. So we have r is equal to 0 and r is less than rows and then r increment. We have the PDRR, this is an array and in a pointer and the malloc, then calls or the columns times size of and then int. So we have the parameter integer. It's surprisingly simple to use this kind of array. For example, if we want to assign 0 to the element lying in the row R, column C, we will do it in this way. PTR tab, then R, C is equals to 0 or null. How does it work? The PTR tab R expression is interpreted as asterisk PTR tab plus R, which means the referencing of the element pointing to the selected row. So instead of using this expression, we can convert that using this one. And that means that that is the referencing of the element pointing the selected row, which is the row R. So the pointer is the reference once more. So the entire indexing expression looks as follows. So asterisk and then inside the parenthesis would be asterisk PDR tab plus R, then plus C. This is simply the desired value of type int. The process of the referencing this element is this expression PDR tab 2 and then 1 is shown in the figure. So here, as you can see, PDRR, which is an array, and 2, the index for that is 1, 2, 3. So here, and 1, we have since column and the row. 2 and 1 is equivalent to 3 and 2. So here, 3, 1, 1 and 2. Here, this is columns and rows of third row and the second column, right? So here is where is the variable array located. The advantage of such array is that, unlike ordinary arrays, every row may be of a different length. This is useful for the algorithms that don't need the entire array to run, but only a slice of it. It refers specifically to a triangular matrices. Such an array can be located in this way. So that would be an example of triangular matrices. This is how it's built. Int row is equals to 5, and then we have a variable r, also in an integer int. Int asterisk asterisk ptr ab. I think this is tab. Ptr tab is equals to int asterisk asterisk malloc rows asterisk size of int asterisk for r or okay, so we have a for loop here, and that would be used for r0. R is less than rows, and then r increment. ptr tab r is equals to int asterisk malloc size of int, and then we have asterisk r plus 1. Pay attention to how the triangularity is obtained. The size of allocated memory block depends on the row number. So as you can see, the rows are having an increment in uh, every rows we have an increment, right? So because of the for loop, and this is our increment, and we have mentioned that r plus 1. So the memory allocated the size of that row. Some declarative traps. Take a look at the following declaration. Int asterisk array 10. In this way, we have declared a variable array, which is a 10-element array of a pointer to data of type int. And now let's look at a seemingly very similar but completely different declaration. Int times array 10. It declares array as a pointer to a 10-element array of type int. Look how the parentheses have changed the meaning of declaration. And now something really difficult. Int times array, asterisk, asterisk array, this is inside of the parentheses, and then 10. The statement creates a variable array, which is a pointer to a 10-element array, whose elements are pointers to ints. Analyze all the three statements yourself and try to identify the rule that determines the proper uh, interpretation of the declaration. We promise we won't leave you alone with this problem. We will spend more time discussing this and even more complicated pointer the declaration later. All right, so as you can see, we have three expression here, three statement here, and that this is the first, second, and third. So how the first, we will talk about it later on the next slide. All right, so we have structures. Structures, why do we need them? Imagine that we, the developers, have the following job to do. We're obliged to design a data structure that can store information about students attending our course. It needs to store the name of each student, the time spent on studying the chapters, and the number of the last completed chapter. We know that the total number of the students will not exceed 100,000. We also know that the most names are rarely longer than 25 characters, and this leads right as the name, the following declaration. So here's the declaration. Char, student underscore name, then we have 100,000, and then 26. The array allows us to store 100,000 names up to 25 characters. Wait a minute. You might say, if it is 25 characters, why did we write 26 in the declaration? We just reserve one more character for the terminating or the closing character. That's all. So let's try to manipulate that array. For example, suppose the first registered student was Mr. Bond. Let's store the information in our array. strcpy, student name, we have the index 0 and then 1. The time spent on the site will be stored as a float. This is not particularly convenient, but we can certainly handle it. The number of hours will be represented as a decimal fraction. This leads us directly to the following statement. Float student underscore time 100,000. We know that Mr. Bond spent 3 hours and 30 minutes studying our course. We will denote in the following way. Student underscore time 0 is equals to 3.5. Note, 3 hours and 30 minutes is equals to 3.5 hours. Thus, it is 3.5. So that would be the declaration of the student time for Mr. Bond. So here in the next slide, the primary objection is that the data regarding the same object or student is dispersed between three variables. Although it should logically exist as a consolidated unit, handling multiple arrays will be cumbersome and error-prone. And when we are forced to collect additional information, we will have to declare yet another array and make a lot of other changes throughout the program. We assure you you won't like it at all. We already know what an array is. An array is an aggregate of elements. The elements are numbered and are of the same type, right? So an array is an aggregate of an element and the elements are numbered and are of the same type. Can we use aggregate whose element could be of a different type? Could they be identified by names, not by numbers? Is it even a good idea? Yes, we can. And yes, it's a great idea. In fact, it was included in the C language at the very beginning. The aggregate we're thinking of it is called a structure. A structure contains any number of element of any type. Each of these elements is called a field. Each field is identified by its name, not by its number. Obviously, the field name must be unique and cannot be doubled within a single structure. We will show you how to declare a structure suitable for our needs and we will explain its meaning. You can see the declaration. You can see the declaration of the structure in the editor. The declaration of the structure always start with the keyword struct. So here in the editor, we can see the keyword struct. And the struct tag is placed after the keyword student in the case. So the student would be the variable for our struct. It's the name of the structure itself. There's a wide accepted custom of composing structure tags with the capital letters only to distinguish them from ordinary variables. So usually we use the variable all caps or in uppercase in order to distinguish them from other variable names. Here comes the open and curly bracket, as in that the field declaration begins at this point. Our structure has three fields. The first is the 26 element array in the type of char, and this name is called name. And the second is float, and it is called time. And the third is int, and it is called recent underscore chapter. So the declaration ends with a curly closing bracket followed by a semicolon after the curly bracket. So that is how we declared a structure. So remember that a structure is any number of any element, any number of any element. Right. So we should emphasize that the previous declaration doesn't create a variable, but only describes the structure we are going to use in our program. We want to declare a variable as a structure. We do it as follows: a struct, student, and then std and t. This declaration sets a variable or a structured variable named std and t. The variable std_nt is a type of struct student. We know that this variable consists of three named fields, but we don't yet know how to access them. As the C language offers a specialized indexing operator bracket for arrays, we also have the selection operator designed for structure and denote a single character dot. The priority of the selection operator is very high, equal to the priority of the bracket operator. This is a binary operator. It's a left argument. Must identify the structure while the right argument must be the name of the field known in this structure. The result of this operator is the selected field structure, and therefore the expression containing this operator is sometimes called a selector. This means that the selector here is std_nt that time results in the selection of the field name time. The type of this expression is the type of the selected field, and this expression is an L value. Consequently, you can use both of these selectors. std_nt that time is equals to 1.5 and float t is equals to std_nt that time. Alright, so in this expression struct student std and t, this is the keyword for structure, and this is the struct tag, the std, the student. This is just a struct tag, and std and t is the variable name for structure. Okay, so every structure must always be always have a structure tag, and it should be in uppercase. And if you want to have its variable name, then it is on different it is in different case or in different spelling. All right, so in this one, this is a selector. This is a binary operator, and we have the left argument. It must identify the structure, which is the variable name. We use std and t here, and the dot is comes from that denotes a selection operator here. So that would be the operator, and time is the name. This right argument, it should be the name of the field, and we call this time it as time. Right. So consequently, you can use both of this operator as the dnt that time is equals to 1.55, and float t is equals to t assigned to std_nt that time. Right. So virtually any data could be used as a structures field, scalars, including pointers, arrays, and also almost of the structures. We say almost because a structure cannot be a field of itself. Structures can be aggregated inside an array. So if you want to declare an array consisting of student structures, we do it in this way. Struct student as TNT 100,000 access the selected fields requires two subsequent operations. In the first step, the bracket operator indexes the array in order to access the structure we need. In the second step, the selection operator selects this desired field. This means that if we want to select the time field of the fourth std and t's elements, we write it as follows: std and t s and 3 the time. We've collected all these assignments. We have been performed for the 3 separate arrays. Analyze them carefully. strcpy stdnts0 dot name then bond. stdnts0 dot times equals to 3.5. stdnts0 present underscore chapter equals to 4. So here we have declared this expression. This statement declares the name of the student. This one is the time, and this one is the recent chapter for the student have been read. Right. So here, as you can see in this one, STD and TS3, the time, we have select the field of the fourth element. this is this is just an index, and the fourth element would be 4. So that would be the equivalent of the uh, selector for time. Declaring the structures. For the purpose of simplicity, we will use a simple structure designed to store the date. It's equipped with 3 fields, each of type, int, name, year, month, and day. Easy to understand names that clearly indicate their role and purpose. The first possible way of declaring the structure is in the editor. Struct date. So the struct tag is the date here, and we have the int variable year, month, and day. So the struct after the curly braces uh, have a semicolon. Both variants are equivalent. That declaration doesn't create any new variables, but only announces to the compiler our intention to use this structure tag to declare new variable. The new variable would be declared, for example, in this way. Struct date of birth. We can use to store Harry Potter's date of birth. A date of birth, that year is equals to 1980. Date of birth month is equals to 7. Date of birth dot day is equals to 31. So that is how we declare the birthday of someone. So we should use another variable, which is what we have learned earlier in the left argument. We have learned earlier is the first one is the name of the arc, what describe the structure, and the second one would be the name of the field. So that is how we did that. We can also use the structure to declare an array of structures, such as this statement: struct date then visits 100. It's also possible to kill 2 birds with 1 stone by defining the structure tag and declaring any number of variables simultaneously in the same statement, like this: struct, then date, and after that would be the curly braces, int, year, month, day, and after the curly braces, date of birth, visit, visits 100, struct date, and then current underscore date. So we can also omit the tag and declare the variables only. Struct, we don't have the struct tag here, but inside our curly braces, we have declared 3 variables in type, year, month, and day, and the day underscore date underscore off underscore the underscore end underscore off underscore the world. In this case, however, determining the type of the variable, the end of the world, uh, becomes troublesome. Without a tag, it has been denoted as size of, then struct, int, year, month, and day. We find it too complex and unreadable compared to size of struct date. So instead of that, we can use size of, then after that would be parenthesis, struct, then curly braces, then declare the int type, which is year, month, and day. A structure could be a field inside another structure. Imagine that we have to extend our student structure and add a field to save the date when a particular student last accessed the course. We can do it the way shown in the editor. It means that we will have to use two subsequent selection operations to go deeper in the structure. First, we select a structure within the structure, and then we select the desired field of the inner structure. This is how it works. Harry Potter dot last underscore visit dot year is equals to 2012. Harry Potter dot last underscore visit dot month is equals to 12. Underscore Harry Potter that last underscore visit that day is equals to 21. So now you should be able to answer the following question: when did Harry Potter visit us recently? Of course, that would be December 21, 2012. All right, so we're in the code in the editor. We can see that we can extend another structure inside a structure. So this field was formed between, as you still remember, we have on the left argument, we have is what is the argument that describes the structure, which is Harry Potter. Then after that will be a dot and a structure which is another uh, structure that describe is last underscore visit, and then we have the field which is this one, time recent underscore and then chapter. So that would be the uh, the expression on how to create an expression inside a structure over a structure. Right, so let's have structures. Few important roles. Structures field names may overlap with the tag names, and this is generally not considered a problem, although it may cause some difficulty in reading and understanding the program. The snippet shown in the editor is completely correct. So here, as you can see, we have the struct, and we have the struct tag, and we have also an int type, and the variable name is track, and the name of the variable structure is a structure. And as we can see, we have the pointer structure dot struct here. So it's definitely this is a correct, correct statement or syntax. But if the reader may read it, it may quiet um, read it in difficulty. So all we have to do is create a good variable name or a appropriate variable name to each of this expression. It may happen that a particular compiler doesn't like it when the structure tag name overlaps with the variable's name. Therefore, it is better to avoid tricks like the one shown in the editor. So here, let's avoid this trick. Struct str int field structure int str. The structure that field is equals to 0 as 0. So it's quite, um, this trick, like shown in the editor, doesn't like the structure tag, and it overlaps a variable name. So two structures can contain fields with the same name. The snippet in the editor is correct. So here we have a structure, but we don't have structure tag, and we have int, and this is f1, and we have a structure name, structure variable, which is str1, and we have another structure. Here is inside we have character f1 and str2 for the name of the structure of the second structure or the variable, and here we have the selector str1 that f1 is equals to 32, str2 that f1 is equals to str1 that f1, which is 32. Structures can be initialized as early as the time of declaration. The structure's initiator is enclosed in curly bracket and contains a list of values assigned up to the subsequent fields starting from the first. The values listed in the initiator must conform to the types of the fields. If the initiator contains fewer elements than the number of the structure's field, it's presumed that the list of is the automatically extended with zeros. If the particular field is an array or a structure, it should have its own initiator, which is also subject to the rule of zero extension. If an internal initiator is complete, we can omit the surrounding curly parentheses. Take a look at the example. Strat date, we have uppercase date, and then date is equals to curly bracket 2012, 12, and 21. This initiator is equivalent to the following sequence of assignments. Date that year is equals to 2012, date that month is equals to 12, date that day is equals to 21. The initiator of this form is functionally equivalent to the following assignments. strcpy, he that name, bond, he that time is equals to 3.5, he that recent underscore chapter is equals to 4. He that last underscore visit that year is equals to 10 to 12. He that last underscore visit that month is equals to 12. Then he that last underscore visit that day is equals to 21. So due to the completeness of the inner initializer, it can be written in the following. Simplified form, struct, student, he is equals to bond, and then we have 3.5, which is the R's 4, and then 2012, 12, and 21. This type of simplification can be also applied in the following case with caution though. Struct student, she is equals to Mata Hari, 12 point, and then we have 12 and then bracket 2012. The internal initiator referring to the last underscore visit field doesn't cover all the fields. This means that it will be equivalent to the following sequence of assignments. strcpy, she that name, Mata Hari, she that time is equals to 12 point, she that recent underscore chapter is equals to 12, she that last underscore visit that year is equals to 2012, she that last underscore visit that month is equals to 0, she that last underscore visit that day is equals to 0. What happens when we apply an empty initializer? So we have struct student nobody, and then curly bracket, and then close and open curly bracket, then it is empty. Here's the answer. strcpy nobody that name, then we have an empty quoted here, and nobody that times equals to 0 0.0, nobody that recent underscore chapter equals 0, nobody that last underscore visit that year is equals to 0, nobody that last underscore visit that month is equals to 0, nobody that last underscore visit that day is equals to 0. Pointers to structures. Let us declare a pointer to the structures of the struct student. Here's how it goes. Struct student asterisk SPTR. If we want to allocate memory for one structure, we can do it in the following way. SPTR is equals to struct student under asterisk malloc size of struct student. As you can see, there's nothing all that surprising here. The SPTR points to a piece of a memory that can be used as if it were a regular structure of type struct student. The selection operator believes its left argument is the structure, while the right argument it thinks is the name of the field. The following the reference identify the entire structure asterisk SPTR. Unfortunately, an expression like the one below is invalid. So this is an invalid expression asterisk SPTR the time is equals to 1.0. This error is caused by a very high priority of the selection operator. It is higher than the priority of the reference operator. So the entire expression will be interpreted as follows. So this is how we do it. Asterisk, then inside the open and close parenthesis SPTR that time. That is, it will be interpreted as if SPTR is a structure. It is not. It forces us to take into account the mutual arrangement of both these operators and to write the expression with additional parentheses. So we have asterisk SPTR inside the parenthesis that time. So that would be that is how we create a structure. The parentheses guarantee that the first operation performed is the referencing, not selecting. Right. So the first, this one guarantees the referencing and not selecting. Because this notation is obviously cumbersome and lengthy, an additional convention was introduced to the C language, which is used to express simultaneous dereferencing and selecting. We do it with the dash, and then we have bracket operator. Note that the arrow is composed of two characters. It is a digraph. It's assumed that the left argument is an expression that evaluates a pointer to the structure. The right argument the right argument is the name of the field of the structure pointed to. The result is an L value identifying the desired structure's field, the reference from the pointer. This means that form pointer, then we have the arrow operator, this one, and dash, and then we have angle bracket field is by definition equals to the form asterisk pointer that field. We can use this form to assign some values to the field of the newly allocated structure. So we have this one and this one. We can both use this expression, and it will prompt in the same meaning, or in the same predator. We can use this information to assign some values to the fields of the new allocated structure. T this is this is strcpy sptr, and then arrow name w sptr, and then arrow time is equals to 0.1, sptr arrow recent underscore chapter is equals to 0, sptr arrow last underscore visit that year equals to 2002, sptr arrow last underscore visit that month is equals to 1, sptr arrow last underscore visit that day is equals to 1. So we have an updated priority table here. So the bracket and arrow dot is included to the highest priority of the table. So let's have unions. Now summing up the topic of data aggregates, we are going to show you a very odd incarnation of a structure named union. The name isn't very illustrative and probably won't give you much idea of where the difference between structures and union is. Syntactically, they're both very similar. You only have to replace the keyword struct with union, and the whole declaration remains valid. The real clue is hidden deeper inside the computer's memory. Take a look at the example in the editor. There are two almost identical declarations of variable named data1 and data2. Respectively, the first one is a structure and the second one is a union. They both have two fields named A and B, accessing the fields in the identical in both cases. Data 1.a is equal to 0, data 2.b is equal to 0. So what is the problem? Where's the difference? We will get back this later. So here we have the struct, and this is data one, named data one. This is a structure, and the second one is a union. They have both integer a and b. So later on the next slides, or in the future slides, we will talk about the difference between structures and unions. In a structure, all its fields are placed successively. Every field has its own part of the computer memory. In other words, each field is a separate world and they don't overlap. Modifying the A field will leave the B field intact and vice versa. This also means that the size of the structure is not less than the total size of all its fields. Note, not less, not equal. In contrast, in a solution, all its fields are placed in the same memory location. This means that the A and B fields share the same part of the memory, or in other words, their contents are indistinguishable. This fact has at least one interesting implication. The union's initializer has to have one element, as there is actually only one value to initialize. It means also that modifying the A field will modify the B field immediately, or rather simultaneously. The program in the editor will output two values, 0 and 1. Can you explain why? We are sure you can. So here's so after running this program, we have two integer here, and that would be 0 and 1. So that's happened. Why? Because as you can see, printf and data1.b, that is under the structure, this one, and data2.b is under the union. So in contrast with structure, we have the probably the data1.b is equivalent to 0, and otherwise in the union, um, we have uh, one interesting fact: in the union has to initialize one element, so it probably contain a one integer here. So there is actually only one value to initialize. So that is the difference between struct and union in this case. When all union fields are of the same type, we can predict the result of the assignment. Take a look at a more interesting example in the editor. The data union is equipped with two fields of radical different types, int and float. As you already know, these types use a completely different method of internal representation. Assigning the A field with the value of 1 won't set the B field with anything even close to 1. We suggest you compile our code and do some experiments yourself. Use really big integers if you want to see some strange effects. Very large negative numbers are even better, but be prepared for a few surprises. Fortunately, 0 is represented exactly in the same way inside floats as in ints. Unfortunately, only 0 has this interesting and curious feature. To summarize union and structure differences, The first, we have the size of the memory in struct. It's the sum of all member sizes in union. Only max member size is important. Only one and also only one member of the union can be accessed at one time, and of course, all members of a struct. Next, a union stores only one value, except some tricky code. A struct stores all the values of the member. You may ask, what's it for? All unions really usable? Are they really needed? We will discuss this issue in the next stage of our education during the C language professional course. For now, sit tight. So as you can see, we have the code in the editor, and we have the first one, the union. Okay, so we don't have struct here, and scanf, and this is an int that declares and that a. So using we have ampersand here because we use scanf, and printf a new line, and then this is a float which is p, and then n, so this is b. So for now we don't have a result in the console because we don't have any declared equivalent for the float. Structures plus pointers equals list. A structure cannot be a field of itself, but any of the structures field can be a pointer to the structure currently declared. Take a look at the declaration in the editor. This is a recursive declaration, as the entity being declared refers to itself, being the declaration is completed. Declaration of this kind offer programmers very intriguing and exciting opportunities. They allow for the defining and processing of data of a very dynamic and changeable nature. Pointers inside structures allow data to relate to other instances in a very complicated way. We are now going to show you an example of this data type of data called a one-way linked list. So this is an example of one-way linked list. So we have the structure here, and the structure tag is element, and we declared an int name value, and we have another struct inside the structure element, asterisk, then that, then asterisk next. The idea of a one-way linked list is based on the observation that if we have a multitude of data, we can link them together, like beads on a thread, and attach the thread to any steady point. We can illustrate it as follows. So first, we design the data to be threaded in a particular way and design what the thread would be. We suggest you imagine something like this. The threaded elements are structures of the same type. Each of the structures will store an integer value. This is only for learning purposes. Real data contained in the list is obviously more sophisticated. We assume that every structure will have a kind of hook which can attach to the next bead in the chain. It will be functional equivalent of a pinhole through which we can drag the thread. The role of coupling will be played by one specific field that can store a pointer to the next element inside the chain. The thread has to be permanently attached, so we need a nail. We assign that role to the pointer variable commonly called head or list header. Look again at the element structure declaration. A field name value will serve as storage for any useful values. A field name next will be used to attach to the next structure in the chain. The first structure in the chain is attached to a head, a variable declared as follows. Struct element asterisk head. The last structure in the chain will be attached to nothing. So we will assign the null pointer value to its next field. Let us imagine a thread with three beads on it. This is what it looked like. So head, then value, then next, then value, next, then value, then next. So this is the flow of how the beads This is the idea of one-way linked list. We are now going to print all the values recorded on the list. This is not as simple as it was for arrays. We can get to any element just by specifying its number. By instead, we must pass through all the previous elements. We want to do this job in the following way. First, we will use the head variable to access the first element. Second, we will use the next field to the first element and access the second element. Third, we will use the next field of the n minus 1 element to access the nth element. The snippet in the editor let us iterate over all the elements in the list and print the value field of each of them. Analyze the example carefully until you are sure that you understand every step. So in this example, we have in every expression that was declared, we have the comment here. So in the first one, we have declared the struct, and the struct tag is the element, and we have declared the int, and the variable name is value, and we have another struct here, and that is and the structure tag is also element. Then we have next. So as you can see, the process of the this one is we will use the head variable to access the first element. So the one-way linked list is created here, this one, after the struct element asterisk head, then the pointer asterisk PDR. So we don't know yet how it was done. We only know the head points to the element number 1. So we have PDR is equals to head asterisk, and then we have PDR points to the element first element now, and we will move it through all elements until we reach into the end. And while we have here the while loop, and we have PDR, if PDR is not equals to none, then print the value is equals to the integer, which is PDR arrow, then the value. So PDR is equals to the PDR, then next is and print done. All right, so that concludes the module 5 part 2, and the so let us close the fourth session of the diverse note front end mobility program. See you in the next and the fifth session, and talks about the module 6. So have a good day and goodbye. Thank you guys.